looking at another resistor circuit, trying to solve the whole circuit here. So we want the current through each resistor and the battery, and the voltage change across rather than shouldn't be through, it should be across each resistor and the battery. So those are your totals, and then your ones for each individual resistor. So I'm going to start by making my chart: R1, R2, R3, and the total, and delta V, I, and R. So we have 1K, a 220 ohm, a 2 kilo ohm. And if I go across this whole thing, I know that I have to drop 6 volts so that I can get back to 0 after I've gone across the battery. So these are the gimmies. We have to see what else we can get. One great thing to do is to help us get the total current. If we could get this equivalent resistance, we'd be all set. So let's try to do that first. It's not a simple series or parallel, but these are in series. So I could turn this resistor arrangement into that and that. So that's my 1K. And these two are in series, so the equivalent resistance for those two together would just be their sum. So 2,220 ohms. Now this is a simple parallel, so 1 over Req is 1 over 1,000 ohms, so 1 over 2,220 ohms, so Req is all that stuff to the negative 1. So that'll be 689 ohms would be the equivalent resistance. So at that point, we would draw the same current from the battery as if we just had the one resistor. If we had all the resistors there, we'll still draw the same current if we replace them all with just this one 689 ohm resistor. Okay, which means we can find the total current pretty easily. So I'm just going to apply Ohm's law to the whole circuit. So I is delta V total, so that's the equivalent to the battery voltage, over the R total, that's the equivalent resistance, which is 6 volts over 689 ohms, which is 8.7 milliamps. Okay. Alright, now let's see what we have. Well, if we apply the loop rule, plus 6 volts across the battery, if I go this way, drop some across the resistor, but then I'm back where I started, so this must be negative 6 volts. So across R1 must be negative 6 volts, which will let us use Ohm's law for R1, calculating the current again. So that's I1 would be delta V across R1 over R1's value. So that's 6 volts over 1,000 ohms, so 6 milliamps is I1. So we had I total, we have I1 and I2. 6 milliamps. Alright, now R2 and 3 are in series, so there's the same currents through them. There's no branches in between. But if we look at the junction rule, it tells us that we had some total amount of current going in, split into 2 branches, I1 and I2. That total has to be the same. This was 8.7 milliamps total. 6 milliamps went down this one, which means I must have 2.7 milliamps going down that one, which would be the same for both. So I can then use Ohm's law to figure out those delta V's. If I apply it to R2, absolute value there is I2 times R2. That's 2.7 milliamps times 220 ohms. Which will give us 0.594 volts. So this is a negative 0.59, I'll just go 0.59 volts. Now there's 2 different ways I can get this. I'll do both. I can do that same thing to R3. So the current going through this is the same as the other one, so that's I2 times the resistance R3, 2.7 milliamps, times 2,000 ohms, will give us 5.4 volts. So this is minus 5.4 volts. So if we look at the loop rule, plus 6 minus right about 0.6 minus 5.4, that does get us back to 0. So either path we take the loop rule is satisfied, which is good. We could have also just used the loop rule to figure that out. So plus 6 minus 0.6, this must be minus 5.4 in order to get us back to 0. Alright, this resistor doesn't figure into it, because if I'm going down this branch, I'm not going down that branch. So loop rule is great for looking at the branches separately. Alright, so now we know voltage across and current through everything in our circuit, including the whole thing together, so we know everything we could possibly want to know about this circuit.